So similar to what we've seen before then, whenever you do regression analysis in R, think R equals robot. So you've got these two separate steps. Run the analysis with the command lm, display the results command summary. So the reason I say that think R equals robot, R is simultaneously very clever and very stupid. It will do exactly what you tell it to do, nothing more, nothing less. So here, as directed, it will firstly run the analysis and that's it. And then secondly, it will display the results once it's told to. So firstly, what you have to do is run the analysis. So the way the R syntax works, as we've seen before, so this is a linear model with rating relating to region, and just call this something logical. Here just call it a.linear model, and then you need the command summary in order to explicitly get R to display the results. So summary a.lm, summary of whatever you've called the linear model in the previous step. And these two things again have to match, otherwise R will get confused. Okay, so we have seen this before. It's got the same rhythm, rhyme and rationale as we've seen in the earlier R examples. Okay, and I think the easiest way of remembering this is just think R equals robot. The thing is very literal. It will do exactly what you tell it to do, nothing more, nothing less. So these regression results in R then, so similar to what we've seen before, what we've done here is we've picked out the t values from the R output, and it's only really the second row downwards where the interesting bits of this are, precisely because usually you always fit an intercept term. Okay, so what we're looking for, the second row downwards, the ones where the p-value right at the end is less than 0.05, and there's only one value here that is significant, the coefficient for the London and Essex region. So this is significant because the p-value at the end, 0.0247, is less than 0.05, and if you were unsure, it's accompanied in R by this asterisk to denote statistical significance at the conventional 5% level. So how you would work this out would be the coefficient is significant because this p-value is less than 0.05, and then the coefficient estimate is negative. So you would work it out in this order. It's first significant and then negative, but then the conventional way of reporting this in the Queen's English would be to say that this coefficient for the London-Essex region is negative and statistically significant. So again, you work it out one way, but it's usually easiest to express it the other way. Okay, and then because this value is negative and statistically significant, the implication is that respondents in this region are harsher in terms of the average ratings that they give. So just to recap then, when we're looking at these regression results in R, the convention would be it's the second row of this table downwards that's interesting. This is because the default is to always fit a constant or underlying average term to the model. And this would reflect that even in the absence of a regional difference, we don't expect the average score to be equal to 0. Okay, so if we take these results at face value, there's evidence P is 0.0247 less than 0.05, that the results for those from the London region are lower than the other regions. Again, precisely because this coefficient is negative and statistically significant. So this has implications for the industrial problem at hand. So the suggestion would be that electricity and water companies that are based in London are systematically disadvantaged by the current system of regulation and the way that customer satisfaction scores determine fines, precisely because results suggest there is this regional bias. The implication being that people in the London region are more likely to give a lower survey rating on average. Okay, so we'll do a professional standard analysis later in the lecture, but this is significant because it's not necessarily obvious a priori that there's a way of quantifying this regional bias. So I wanted to just say a quick note here on reparameterizing the model. It's one of the few occasions here with the regression model where I would suggest not fitting a intercept or constant term to the model. So this is to do with the peculiarities of this example, and in this case the estimated effects of the regional bias can be better presented by reparameterizing the model without the constant term. Okay, this is precisely because of the peculiarities of this problem. And one of the reasons I wanted to sort of emphasize this is I do think it sort of says something about some of the intricacies of communication. Sometimes me and my co-author, both good professional academics, we got the paper finally published in the end in an academic journal. We didn't necessarily use the best way of communicating this information. So it turns out the best way to sort of parameterize the model and express this regional bias is to suppress the constant term, and in R this is achieved by including a -1 term into the list of X variables. So this is just telling R fit the regression as normal but omit the constant term. Okay, and then exactly as you've seen before, think R equals robot, do exactly what you tell it to do. Firstly, run the analysis, do a computation, call it something logical, and then display the results when explicitly asked to using this summary command. Results in R then, so this time there's no constant term. Don't think it's necessarily so meaningful here to look at the statistical significance. In each case it's kind of obvious that the average score for each region will not be 0 out of 5. Indeed, the lowest possible survey rating that you can be given is 1 out of 5. It just gives you an indication of what the slight differences in the average score by region are, and what you should see here is that the results are slightly lower for the London region. So you need the other parameterization to really test that there is in fact a statistically significant difference, but this is probably the best way of actually articulating what that difference means from a practical perspective. Okay, and this is a slightly unusual example in the sense that because of the peculiarities of the problem, it's actually worth fitting the regression model without a constant term in this case. And again, I think this is sort of sufficiently subtle that we didn't think to parameterize the model in this way for the version of the paper that was formally published in the journal. Okay, so I think this does emphasize here that the name of the game is communication, and sometimes even the professionals are not guaranteed to get this exactly right. Okay, so the name of the game is always communication. It's not just about being clever per se. So interpreting these regression results then, so the numerical results should be the same under either parameterization. It's just it's easier to sort of see this if you use the second parameterization, because then you have the listing of the average score by region produced automatically. And how this works then, so both parameterizations have some value. You have to use the first parameterization to test for the regional differences. In this case, the significant values indicate that the London scores are generally lower than the benchmark score for the first East Midlands category. Okay, but it turns out in this case, the second parameterization is the easiest way to present the estimated average score by region. In this case, the significant values aren't really very meaningful. They just indicate that none of the regions is the average survey rating equal to 0 out of 5. The numerical estimates obtained suggest only minor differences in the average scores for customers from different regions. However, these results do show you that the results are slightly lower for the London region compared to the other regions of the UK. And just to sort of re-emphasize here that the estimated customer satisfaction scores should be the same under either parameterization. Okay, and I just wanted to sort of go through a numerical example to demonstrate that this is indeed the case. So to just show you here that the different parameterizations give you the same answer, so I wanted to concentrate for the sake of argument London region. So the second parameterization shown on slide 2.11 shows you that in this case the average customer satisfaction score for the region is just 3.92497, and you can just read this straight off the computer output in this case. So under the first parameterization, the average customer satisfaction score for the London region can again be read off from the regression equation, but it's slightly different here. So how the first parameterization works is that the average score is given by the intercept plus a London adjustment. So if you read this off from slide 2.8, the intercept is 3.989932, the London adjustment is minus 0.064965. So this does give you the same average regional score as the second parameterization. In this case, what is happening under the first parameterization, that because this minus 0.064965 parameter estimate is negative and statistically significant, this does reflect in this case that the average London score is lower than the benchmark score. So I wanted to go through here the R commands for the second industrial problem that I wanted to look at in this lecture. So similar to last time, the best way to do this is to take the .text file available on Canvas, save this to your USB drive, and read this data into R using the command read.table. You need to make sure that you have the right file path. So there, my USB stick is the E drive. You might need a slightly different letter for your example working on your computer at home. So what we've eventually done here is rating is the first column of this data set, product is the second column of this data set, region is the third column, and then the region missing variable is the fourth column. And then what the region missing variable is in the fourth column is 0 if the regional data is given and 1 otherwise. And the easiest way to subset this data is to restrict the rating variable to those values where the region isn't missing, subsetting it with the region missing less than 1. And we've done exactly the same with the product and the region variables, so we're restricted in both cases to cases where the region missing variables is less than 1. So in both cases now we've got product and region data with the regional affiliation of the respondent given. So I want to just emphasize here that these R subsetting commands are very flexible and very useful, and we've got here, I think, for the first time, a genuinely meaningful data example where you need higher level computing in order to process the data. Okay, just menu driven commands in Excel won't work very easily for a data set of appreciable size. So what we're doing here is in R generate the sequence of high values using this thing here times the rating and 3, medium values using this thing here 1 times equals to 3, low values generated in, we should say there, rating less than 3. Okay, so what is happening in each case is that you get a sequence of values that take the value 1 if the observation belongs to that category and not otherwise. And all this is just a very convenient trick in R to convert from logical data to numerical data, with data in the numerical format. Okay, and this is the easiest way to use this logical data, get it into a numerical format that you can then fit a statistical model to. So further considerations for these sorts of probability models, so exactly the same as we've seen last time. So to fit a binomial generalized linear model in R, you need the data organized in columns of successes and failures. So strictly speaking as well, these binomial models are formulated for occasions where you only have 2 categories, for instance yes, no, successful, unsuccessful, male, female, etc. Now our big data example now contains 3 categories, so you now need 2 equations. So the 3 categories are high, medium and low, and the basic idea is that if you have one equation to describe the probability of being awarded a high score, and one equation to describe the probability of being awarded a low score, then those 2 equations should be sufficient to describe this 3 category system. So you can fit a third equation, but this should be redundant, and what I wanted to sort of do in this lecture is still fit this third equation. So even though this should be redundant, it's still worth doing this as an extra practice for modelling in R, and just gives it an extra check that the rest of our conclusions are in order and we haven't made an obvious mistake. Okay, so we still need to organise the data in terms of successes and failures exactly as we did last time.